That last variation of the area between two curves involves a different, it's another integral, but it's a different kind of an integral. This is called a dy integration. And so let's sort of review what the steps we do for a dx integration are. In a dx integration, you have two functions. You have f of x and g of x. When you set up the integral, essentially what you're doing is you're drawing in a representative rectangle. Okay, and this rectangle has an area, base times height. The base is always the dx because it's a small horizontal change. And the height, we do the top minus the bottom. The top is f, and the bottom is g. So this is the area of one of these little rectangles, but then what we have to do is add all the rectangles up between this x value and this x value. And the way we add them up is by integrating. So we integrate from x equals a to x equals b of f of x minus g of x, and finally dx. So notice there's a lot of, x's going on. You got x equals a, x equals b, f of x, g of x, and d of x. If all of these things match, then you're good to go for evaluating your integral. Now, here's a type of problem where you can't really do a dx integration, and it makes more sense to do a dy integration. Here are two relations. Notice that no longer are we dealing with g of x, but now we're dealing with g of y. And so these two things are both functions of y. Sometimes you're given a function in terms of x and then you have to solve for y. So for example, in the second one, this might have been given to you as y equals x minus 1. However, because you are given a different function of dy, you would have to solve this equation for solve this equation for x, because that way you'll get the function in terms of y, and that would be the y plus 1. So we'll go through like when you should do a dx and when you should do a dy integration, and that'll become more clear. But if you have functions with y's in them, then you're probably going to do a dy integration. The best thing to do is, let's go ahead and graph these. So to graph to graph y functions, you sort of you can plot points, that's a good way, or you sort of just flip the x and y axes like 90 degrees. So the equation y plus 1 will have an it'll have an x-intercept of positive 1 and then a slope of positive 1. So here's our function f of x. And then the function 3 minus y squared is a parabola. It's y squared. It opens, instead of opening up or down, now it's going to open left or right. The positive direction is to the right, so because it's negative, it's going to open downwards, and then it has an x-intercept of 3. So our parabola starts here, and then it opens leftwards. So that is our parabola. And then the region that we're looking for is the region trapped in between here, like that. Now, in this case, we can't do top minus bottom because we have functions in terms of y. So instead of doing top minus bottom, we're going to do our rectangle like this. Here's our little rectangle. The height of the rectangle is now a small change in y, so the height is dy. To find the base of the rectangle, we need a positive number, and so to find a positive number, you take the more positive x value and subtract the less positive x value. So in this case, we're going to do right function minus left function. And in this case, the rightmost function is g, so we're going to do g minus f. Okay, we're almost done. Let's finish setting up the integral. So we're going to have the integral from a to b. Again, we haven't found out what those are yet. And then we're going to have g of x, which is parentheses 3 minus y squared, minus parentheses, remember to do this, y plus 1. And then instead of a dx, we're going to have a dy. As a quick check, notice that, hey, you have a y here and a dy, so far we're good. The next step is to find the intersection points. We do this the same way that we did last time. We set the f and g equal to each other. So we'll have 3 minus y squared equals y plus 1. Moving the y squared and the 3 over, I'll get y squared plus y minus 2 equals 0. Factoring this, I get y plus 2, y minus 1 equals 0. And my two solutions for y are negative 2 and positive 1. So back on our picture, that means that this y value is negative 2, and this y value is positive 1. So for my limits of integration, I integrate from y equals negative 2 up to y equals positive 1. Notice that these limits are now y values and not x values because y, we're doing a dy integration. From here, we have our integral negative 2 to 1 of 3 minus y squared minus y plus 1 dy. From here you would go through the integrals, or go through the steps to integrate, plug in the 1, plug in the negative 2, subtract them, etc. I'm not going to do that, but you get the gist of how to set up a dy integral.